So hello everyone, welcome back to another particular lecture of our reagent chemistry course, and this is class 33 and this is the last lecture of our reagent chemistry course where we will discuss about oxidative cleavage. Now oxidative cleavage says that if you have this type of carbon-carbon bond, you will to cleave this particular carbon-carbon bond by oxidatively by using certain reagent, and in this particular class we talk about those reagents. But before that we have to learn that the definition of oxidative cleavage. So the oxidative cleavage is a chemical reaction where a double or triple bond in an organic molecule is broken and the molecule is split into smaller fragments. That means we are just splitting that carbon-carbon bond by using oxidative pathway. Now in this particular case you have to learn two type of oxidative cleavage that is very useful, as well as in exam point of view that is very important. That is the oxidative cleavage of diols and oxidative cleavage of alkenes. Diols suggest that you have this type of compound and you want to break this particular carbon-carbon bond, and alkene we know that this particular bond breaking. So in case of oxidative cleavage of diols, there is two famous reagent has been used. One is the NaIO4 and another is a PbOSe whole 4. These two reagent has been used to break this type of diol. Okay, and in the case of alkene, there is a three different reagent. The one is the O3, that ozone that breaks that particular alkene bond via ozonolysis. We'll discuss that, as well as the two name reaction is there, Lemieux-Johnson oxidation and Lemieux von Rudolph oxidation. So these two we'll discuss in this particular class. First, we talk about the oxidative cleavage of diols. Oxidative cleavage of diols, sodium periodate or H5IO6 can be used to cleave vicinal diols into two carbonyl compound or into a single compound with two carbonyl groups. That means if it is a open chain type of compound, then it form two different compounds, and if it is a single cyclic type of compound, then it will form a single compound with a two carbonyl group that we will discuss in the particular examples. Okay, so now you can imagine that this is your 1,2 diol and this particular bond will be broken. So what happened that NaIO4, it will form this type of 5-membered cyclic ring, and after that this particular cyclic ring breaks and it will form this type of this particular carbon-carbon bond breaks and we got two carbonyl groups here. Similarly, in the case of trans diol, it may be possible to do this type of transition state if those are close enough or there is a lesser steric hindrances there. But however, in the case of cis product, the reaction rate will be much higher over the trans. Okay. Now let us talk about another example, that NaIO4, it can cleave 1,2 dicarbonyls. That means if you have this type of compound, there is a 1,2 dicarbonyl present here, then it will break this bond also and will form two different carboxylic acid group. Similarly, if you have this type of combination, then NaIO4 breaks this particular part, so we got a corresponding acid part here, and this will form the carbon dioxide and H plus is formed. However, there is certain limitation while using sodium periodate, that is that I already discussed about in the previous slide, that in the case of trans it might be possible to break this way because somehow it might get adjusted to form this type of 5-member cyclic ring and then it will get broken. But in the case of this particular compound, if we draw it like a transdecalin format, then you can find one OH is here and one OH is here. That means there is no possibility to form the 5-member cyclic ring here. So that means this type of compound, this particular bond will never be broken by using NaIO4. Now let's talk about another particular reagent, that is ledtetracetate, that means PbOSE whole 4. This is also a common reagent for the cleavage of diols. However, it is a strong oxidant and can react with a variety of functional groups. For example, you can find here, this is a D-mannitol. Yes, this is a protected form of D-mannitol. Now this particular D-mannitol, here you can see that 2 chiral center has been there. Now treated with the lead tetraacetate, we successfully cleave that particular bond and we form this type of chiral compound, and this is very important uh, starting material for a different natural product synthesis. Okay, and this lead tetraacetate also uh, do this type of cleaving by 5-member ring. Also it can be react via the stepwise manner. For example, in the previous case I have told you that this type of compound cannot be cleaved, that particular CC bond cannot be cleaved by the NaIO4, but it can cleave via PbOSE. How? Because PbOSE is actually coordinating with this, and it liberate one OSC minus. That particular OSC minus captures this proton and generate a O negative here. Then O negative come here, these bonds cleave and this will go out. So this particular compound cannot be oxidative CC bond cleaved by NaIO4, but it can cleave via PbOSC whole 4. This is the reaction. Okay, now we are done with this particular 1,2-diol. Now let us talk about the oxidative cleavage of alkene by ozonolysis. I hope that ozonolysis reaction you are familiar with this, because the ozone is the widely used reagent for the oxidative cleavage of olefin, and the particular reaction is considered to be 3+2 cycloaddition of oxygen into the alkene. Now let's dive into the mechanistic pathway of this particular reaction. Initially, this is the structure of ozone. Now this ozone react with the corresponding alkene via 3+2 cycloaddition. That means this particular negative will actually initially attack here, and then this double bond attacks here, and this particular oxygen is electrophilic, so this particular bond will go there and to form this intermediate. Now this intermediate called as the mole ozonite. Now here if you see that there is a 2 OO bond is there. Okay, now we know that hetero bonds are not that much stable over the CC bond, so this intermediate is unstable, so that it actually breaks apart. How it is breaks apart? That this particular lone pair goes here, this goes down there, and this is back to form this type of 2 different intermediate in situ. That is called as a carbonyl oxide. Now these 2 intermediate are actually tends to rearrange to form ozonide, which is much stable over mole ozonide. How? That this particular negative actually attacks in this particular carbonyl carbon center, this goes up. Okay, so we'll discuss in the next slide. Here you can see that this negative charge actually attacks here, and this goes up, this negative will actually attack in this particular carbon center. The driving force is to stabilize that particular oxygen center to form this particular ozonide. Now when we generate that particular ozonide, now you have variety of option that what you want as your final product. By twerking different reactive workup condition, you can might generate a carbonyl, might generate a alcohol, might generate an acid compound. Okay, now if you treat that particular ozonide with reductive workup by using dimethyl sulfide or iodine or triphenyl phosphane zinc acetate, then it will show a reductive workup and you will obtain the final carbonyl compound, that is a ketone compound. Okay, ketone or aldehyde compound. However, if you want to go direct alcohol stage, then you have to do a reductive workup by using lithium aluminum hydrate or sodium borohydrate. That means a hydride donator is required to form ozonide to their corresponding alcohol. And if you want oxidative workup to get ketone or carboxylic acid, then you have to treat that particular ozonide with H2O2, Ag2O, that is a silver oxide, CrO3, KMnO4 or O2. That means the oxidative agent has been required to do that type of oxidative workup to get ketone or carboxylic acid. Now let us see certain example of that particular reaction. For example, you can find here, this is ozone and this is the starting material. Obviously, ozone will react with this double bond to form ozonide. Initially it will form mole ozonide, followed by it will form ozonide via rearrangement. After that you can see there is a H2O2 is there. H2O2, when you see H2O2, the reaction that clicked in your mind that it is doing a oxidative workup. See here, oxidative workup H2O2. That means at the end product it will form either ketone or carboxylic acid. Now as expected it will form a ketone because here is a no chance to form the carboxylic acid. However, in this particular part we will form the carboxylic acid. Similarly, for this particular reaction you can find here that in presence of O3 it will also form mole ozonide, then ozonide. After that you can see here the reductive workup is doing, that is the dimethyl sulfide has been used. That means it will form a carbonyl compound. Like here it will form a O, that is a ketone, and here it will form a acetaldehyde, aldehyde. Okay, now let us move to the two named reaction where the oxidative cleavage of alkane has been observed. First one is the Lemieux-Johansson oxidation. It is a two-step oxidative cleavage method where the reagent has been used is the catalytic OSO4 and stoichiometric NaIO4. And how it is two-step? Because in presence of catalytic OSO4, that alkene is converted to 1,2-diol and followed by treating with the NaIO4, it will form the corresponding that CC bond cleavage takes place. Okay, here actually NaIO4 has dual role in this particular reaction. The first is obviously breaking the carbon-carbon bond, and if you remember about the OSO4 based cis dihydroxylation formation that I already discussed in I think class 19 or 20. So here you can find that during the course of reaction OS8 are actually converted to OS6, and this OS6 are not the active catalyst, so it requires a terminal oxidant to return back OS8. So NaIO4 actually acts here as a terminal oxidant, so that actually that OSO4 has been used here in the catalytic amount and NaIO4 has been used as stoichiometric amount. Okay, and this is a fair alternative of O3 base cleavage. So this is the reaction you can find here, that this is the alkene react with the catalytic OSO4. in room temperature to form the dihydroxylation. The diol formation takes place, and followed by NaIO4 treatment, we got this particular CC bond cleaved. Okay, and you can find here that this all are reaction in the room temperature reaction, where in the case of ozone we have to do a lower temperature reaction. So it is a fair alternative of the O3 base cleavage. However, this particular reaction also have a drawback. Since it reacts use the OSO4, OSO4 is practically toxic and volatile. Okay, that's why to eliminate the OSO4, there is a upgradation of this particular reaction has been introduced, that is the lemieux von rudolff oxidation, where they actually throw down the OSO4 and bring that KMNO4. KMNO4 is also acts as a dihydroxylation formation, the diol formation, and the similar mechanism has been observed. And interestingly, this reagent condition, because KMNO4 is also a oxidant here, so the final product formation is acid, and in the case of previous one, you can find a carbonyl compound here, but in the case of this lemieux von rudolff oxidation, you will form acid over aldehyde as a final product. So for a simple example, you can find here, this is the most classical example that I have found in the book. So here you can find there is the alkene is there. Now in presence of lemieux von rudolff oxidation condition, that is NaIO4 stoichiometric and KMNO4 catalytic amount, the final product is the acid. Whereas in the Lemieux-Johnson oxidation condition, where the OSO4 and NaIO4 combination has been used, the final product is aldehyde. So with this, we have to officially end the reagent chemistry course. I hope that you will learn a lot in this particular course, and that's all from here, and then we will discuss about some kind of reactions and examples of this particular topic. So thank you all. We'll meet on some other chapters lecture. So thank you.